In this video, I'm going to introduce us to the alcohol functional group, also sometimes called the hydroxyl group. And so we've obviously already encountered alcohol groups in previous videos, but when we go through these functional groups in videos sort of dedicated to them, we look at it more thoroughly and more systematically. And so that's what this and the next several videos after this are going to do is look at alcohols and look at the reactions of alcohols. And so this one's going to be a introduction to it. So I'll talk a little bit about the physical properties and then some of the ways that we've already encountered to actually make alcohols. Before the next video, I will get into sort of, I guess, more newer reactions to form alcohols. All right, and so when we have our primary alcohols, so we can have methanol, so it's just methane, and you put an OL at the end of it instead of an E. Same with ethanol, ethane, but instead of an E at the end, you put an OL at the end, so ethanol. Then we have 2-methyl-1-propanol, so we see that the hydroxyl group here, the alcohol group, is taking priority over the methyl group here. Then we also have something like benzyl alcohol. So this has the benzene ring, then a carbon before we get to this alcohol group. So that is still a primary alcohol. This one here, actually, this should be, we can see this should actually be a secondary alcohol, don't we? Because it's bound to a carbon that's bound to two other carbons here. But what we can see here, so we have the Z4-chloro-3 butene 2-ol, and so the alcohol group here is taking priority over this chlorine. So that's why if we start numbering from here, this is on the second carbon, and so it's the 2-ol, and then we have the alkene group right here, and so that's our 3-butene because this is on the third carbon, then the 4-chloro right here. This is this alkene here, this double bond is in the Z formation. But as I said, this should be a secondary alcohol, which is the next ones we'll look at right here. And so this is an alcohol group bound to a carbon that's bound to two other carbons here. And so one that you might be familiar with and possibly even have it in your house is 2-propanol, or called isopropanol, which is often used in rubbing alcohol for, disinfecting things. We can also have cyclohexanol. And so again, that's just the naming convention. We put the cyclo because it's a cyclic thing, and then we have hexane, and then just replace the E with an OL at the end. And again, this one should actually be in the primary alcohols we can see here. So this is an alcohol bound to this primary carbon right here, but this is trans 2-pentene 1-ol. So this one should actually sort of be switched around with that one because this one up here is a secondary and this is a primary right here. And so we see that this has the alcohol as the one carbon here, so that takes the priority over that double bond, and it's a trans double bond, so it's trans 2-pentene 1-ol. And so we can also have diols, which means that it has two hydroxyl or alcohol groups on it. So for instance, right here we have 1-cyclohexyl butane 1,3-diol. So we have the cyclohexyl group right here. Then we have this butane group right here with two alcohol groups on it. So it is the butane group here is coming off of what we're calling the one carbon. So it's 1-cyclohexyl butane, then 1,3-diol. And we can have this right here. So this is a trans-cyclopentane 1,2-diol. And we can have this vicinal diol here. So that's going to be two alcohols on these carbons right next to each other. And so this is called a glycol right here. We could also have tertiary alcohols, so we could have something like 4-propyl 4-heptanol. So if we see here, we have 3 carbons and then this one, so our main chain will have this times 2, and then this carbon here, and then there is a ethyl group coming off of it, off of the fourth carbon and this hydroxyl group coming off the fourth carbon. So it's 4-propyl 4-heptanol. We have 2-methyl 2-propanol, so that's what we have right here. So this and this coming off of that second carbon, we could call this 1, 2, and 3 here. So 2-methyl 2-propanol. And we can have this coming off of a cyclic group like this. So we could have 1-methyl cyclopentanol. So this, well, this should actually be cyclohexanol, right? So this is not a cyclopentanol group. So this should be cyclohexanol right here. So let's say 6-member ring. We have the alcohol group and then the methyl group here, both coming off of that 1 right there. And we can also have what are called phenols, which are just alcohol groups coming off of these aromatic rings. So this is just a standard phenol, but we can put other groups onto it. So we can have 3-methylphenol. This one is called hydroquinone, and so that's sort of a, I guess, common name for it. Then we could have, this 3,5-dibromophenol, which here again is showing that the alcohol group is taking precedence over these bromines. So this is on the 1 carbon group, and then we number it. So starting here, 1, 2, 3. So that's the 3 here, then 4, then 5, and 6. So we have another one coming off the 5 right here. All right, so some physical properties here. So we have melting points, boiling points, and densities here. And so I've put some red boxes around just the sort of standard alcohols here. So just the alcohols, so methanol, ethanol, propan, 1-ol. So that's the 1, 2, and 3 carbon chains with an alcohol group. Then the butanol right here, pentanol right here, hexanol, and then the heptane to decane all right here. And so we can see if we look at these that the boiling point of these kind of goes up as we increase the number of carbons on here. So we can see these boiling points going up for each of these. And so that, is to be predicted, because if every time we add another, carbon onto here, it's going to have more of those van der Waals forces or London dispersion forces to help those sort of stick together better here. And we can also see if we have like the propan 2-ol and the butan 2-ol, we can look at these. And so this has the propan 2-ol has boiling point of 82, the butan 2-ol of 100, and so on. And so, we can look at these. I mean, this is obviously something you're not going to need to memorize, even if you're taking like an organic chemistry class. But, just looking at some trends on this. And so, you can look at this, on your own, pause the video or whatever if you want to look at it more on your own to try to pick out other trends on here. And so alcohols, unlike ethers, do have this hydrogen bonding. And so we can see here if we have something like ethanol compared to dimethyl ether, which have the same molecular weight here, that the alcohol has a much higher boiling point than the ether right here. And of course, both of them have higher boiling points than a similar molecular weight alkane right here. So this propane here. So that's because the ethanol can engage in these hydrogen bonds, where the dimethyl ether is going to have, it's going to be a little bit more polar because we do have this dipole moment here that's a lot larger than what we have on the propane right here. All right, so then solubility of alcohols in water. So we can see, following that sort of rule of, having less than 4 of our carbons in our carbon chain here is going to be miscible or soluble in water. Then if we start getting too large here, then we start seeing the solubility go down as we go through here up to the N-hexyl up here, which is quite insoluble in water. Where phenol is a little bit more soluble. So we can see right here that that is about as soluble as the N-butyl group right here. Then, of course, hexane 1,6-diol becomes miscible again. So the hexane 1,6-diol would be 6 carbons. So 1, 2, 3, 4, 5, 6. Then it would have these hydroxyl groups on it right here. And so this once again becomes miscible in water because now we have these two places on here where we can form hydrogen bonds with our water. Kind of the rule of thumb is, especially when you're looking at the sort of linear chain alcohols, that if you have fewer than 4 carbons on it, then it's going to be miscible in water. We can see here that if we have this as tert-butyl rather than just like N-butyl right here, that it makes it miscible in water. And so that's because we are, instead of having like a chain of 4 carbons, we have something that looks like this. So these don't stack together as well and engage in those London dispersion forces. All right, then we can look at the acid dissociation constants of some alcohols. And so I've talked about this or mentioned this in previous videos. So things like our methanol and ethanol have a pKa of about 15.5 to about 15.9. And so those are, pretty weak acids. So those are fairly weak acids. If we start adding some groups on here like chlorine that are more uh, electronegative, then we get those inductive effects and they become more acidic. But if we start adding more and more carbon groups on here, we see that we actually get less and less acidic, and that's actually inductive effects with the carbons, which are sort of putting even more electron density into the oxygen. Then, of course, the phenol is going to be even more acidic because it has that resonance stabilization for the oxy anion that's formed. And we can compare this to some other acids here. So water being pKa of about 15.7, then acetic acid, which has that resonance stabilization of the conjugate base, is now going to be even more acidic. And then we have the hydrochloric acid, which is a very strong acid here. And so we can make these alkoxides here using this technique. So we can put our alcohol here into sodium metal, so that will reduce the oxygen here, so the oxygen will oxidize the sodium, and so we end up with this right here, and then we lose hydrogen gas. So ethanol reacts with sodium metal to form sodium ethoxide, which is a strong base that we have seen in previous videos can be used for elimination reactions. More hindered alcohols like the 2-propanol or tert-butanol react faster with potassium, since potassium is more reactive than sodium. And we can see here this is why the phenol is more acidic than, just like a primary alcohol, for instance. That's because we have this resonance stabilization that we can see down here, where the negative charge on that oxygen can be shared sort of throughout that ring there. All right, and so as I said, I'm going to quickly go through some of the previous alcohol syntheses that we've already seen in videos that I've already done in previous videos, so I'm not going to spend too much time on the mechanisms here. So we've encountered the nucleophilic substitution of an alkyl halide, so we can bring in a hydroxide here that will attack this carbon right here. This will start to leave so that we get this transition state, and then we get the inversion here, which is now an alcohol. And what we're showing on here is a primary alcohol because this SN2 has to be done on a very unhindered carbon. So this is a primary alcohol right here. We also have the acid catalyzed hydration of alkenes. And so that's where we bring in, something like an acid here. So we have like an H plus, and this will go and attack that so that we end up with something of an intermediate that looks like this. So we have our H plus right there, kind of bound to both of them. Then we can bring in the water right there and have that go up there. And so we end up with the Markovnikov orientation. And so that means that the hydroxide here is going to be on the more substituted carbon. So we also saw the oxymercuration, demercuration of alkenes. And so that is using this mercury acetate right here. And so this will produce this as an intermediate. Then we bring in our sodium borohydride, and that will remove this mercury species right here so that we get the Markovnikov orientation addition of that hydroxyl group. So hydroboration oxidation of alkenes will give us the anti-Markovnikov orientation. And so we bring in 3 of these for each one of our BH3THF, which is usually the form that this is used. And so we put this boron species, this borane species on here on all 3 of these. Then we put in H2O2 and hydroxide to oxidize this, and we end up with 3 of these in the anti-Markovnikov orientation in the syn stereochemistry. So anti-Markovnikov meaning that our hydroxyl group here is ending up on the least substituted carbon. So we can also do syn hydroxylations of alkenes using these oxidizing agents like osmium or tetroxide and potassium permanganate. And so we will end up with 2 hydroxyl groups on here. So we end up with diols here with it in the syn orientation here. So they're added to the same side of our alkene. So we can do an anti-hydroxylation of alkenes. So we bring in a peroxy acid, which will give us this epoxide right here. And so then we can bring in a water, so H2O will attack that. This will go here. And so we end up with an anti-hydroxylation here. So a diol that's in the anti position. And lastly, we have the addition of acetylides to carbonyl groups. And so we are turning this carbonyl oxygen here into the alcohol. So we can bring in the acetylides, so that will attack right there. Those electrons move up to there. We could then add water into this to protonate this, and now we have an alcohol. And so, yeah, those are the ways of making an alcohol that we have already encountered in previous videos. In the next video, I will be talking about some ways of generating alcohols that I have not yet covered in previous videos. And then after that, I'll be looking at some reactions that you can actually do with alcohols. And that might take several videos after that. So the next several videos now are going to be focusing on the alcohol or hydroxyl functional group. But anyway, I hope you found this video helpful, and I will see you in the next one.